There we go. All right. So, welcome to the third session of the 7130 introductory series. If you haven't done one and two, definitely go back and do that. This is not the session that you want to jump straight into if you don't have the basics of how these particular devices work. So there's a few topics we're talking about today. It's going to be the two biggest applications that are used. The first one we're looking at the slide in front of me is called MetaMux, which is our multiplexing application. The following one will be MetaWatch, and then we'll do a little bit more with how to get a show tech support, what's in them. So without further ado, MetaMux. Um, so we talked about this a little bit yesterday when we were kind of going over regular application overviews. MetaMux was built around the idea of um, it's easy to fan traffic out from one source to multiple different receivers. However, it's much harder to take the return traffic from all those different receivers and get them back to that original host. And that's where this idea came from. So we put an FPGA inside the 7130s and we wrote a program to do multiplexing, right? Or packet aggregation or muxing or whatever you want to call it. And so the whole idea there is that you can have multiple streams of data coming into the FPGA, and the FPGA will organize that data, multiplex it, mux it, whatever you want to call it, and send it out whatever interface we want to send it to, a single feed. Um, so currently we have a bunch of different modes that are in the MetaMux app. You should know that they're all really only compliant with 10 gig. So technically we have a 1 gig version of MetaMux and there's other specific use cases, but at a high level overview, just be aware that this was designed for 10 gig. It predominantly only supports 1 gig. And the moment someone talks about doing not 10 gig with this application, it should set off red flags, at least for you to go heavily looking into what limited use cases we might be able to support are. Aside from that, it does support a bunch of different configurations with a bunch of different sized multiplexers and queuing options. And what do I mean by sized multiplexers? Well, in this diagram in the upper right here, we've got 8 total SFPs. We've got front panel SFP. Our second panel goes over to probably the actual trade server. And my guess in this particular environment would be we'd be multiplexing like 7 connections together to go out one. So a total of like 8 ports in use. And we have a lot more ports on these devices. So we could do multiple sets of 7 ins and 1 out, or we could do like 4 ins and 1 out. And we could do that even more times because, if we have 40 ports on a switch, we could do that in theory 8 times. And so you can see a list of by going into the MetaMux configuration. And we talked about this a bit yesterday. It's show modes. Again, you won't see that from the base CLI. You have to go into the configuration of the application. Then you can look at all of your available modes. We do have 2 major release versions of MetaMux. I'm going to say original version is actually version 2. It runs on all of our C and K series FPGA devices. And then version 3, which is the current version, and is running on the E and L series and future series devices as we get them. All of these modes support 16 kilobyte queuing buffers. So there is some buffering that gets involved when you start muxing traffic like this. That said, this really isn't a whole lot of buffer space, right? Not comparatively to like MetaWatch. So it's all still very, very quick. Again, the port-to-port latency through a mux is only about 44, 45 nanoseconds. It's still very quick. Some example application modes are in front of us here, and we looked at this in the CLI a little bit yesterday. Like this top example is a single 32 into 1 multiplexer. We take 32 inputs, we multiplex it into a single output, right? If you see a prepended thing, like actually that's not prepended. I don't have a prepended example. Oh no, 4 times 8. Yeah, that's what it is. So our prepended example is like a 4 by 8, meaning you have 4 8 by 1 multiplexers. If you denotes like the plus here at the end, it means that we have a combination of different types of multiplexers. We have 2 8 by 1s and 1 16 by 1. And when you run show modes, it'll actually list all of these descriptions. So you don't have to memorize this. This is just some examples of the different things that you can do. This is what it actually looks like in the CLI. I didn't take this particular picture, so hopefully the black on green isn't painful to the eyes. I think I'll probably replace it with something that feels like it fits down the line, but here we are. You go into your application, you see here that we had exited out to show, the differences. You go to configure application metabooks and then list modes. There's no hyphen or anything there. Those are two separate. Latency numbers. Yeah, okay. So those are the K and C, which were way higher than I thought, but that's okay. So we have a number of different published numbers for latency, and it depends on several things, platform as well as modes. When in doubt, just check the manual. It's going to give all of these values because our customers all desperately want to know this. So it's public facing already. At a high level, the older the device, the higher the latency, right? So you have the K and C series, which are running Metamux 2.x, are 60 to 90 minimum latency to 85 to 116 on the high end, right? And then the E and L series, much faster. Like we halved from the K series, down to either of these really. So big differences there. How do you configure these? So we use this concept of application ports. Now, these are virtual ports that are used by the FPGA so that we can control what data goes into the FPGA and which data goes out of the FPGA, and how do we control that and figure it out, right? So in this example, we have a 4-port MUX. So we have a bunch of FPGA ports, and in this case, when we look at our interface statuses for the MUX, we'll see that we have an AP 1, 2, 3, and 4 in, and that we also see that AP 1 is out. Now, what that means is whichever port has the out, that's not configurable. That is statically defined, or not statically, yeah, statically defined. You can't change which port your out port is unless you just change modes. But in which case you're going from, say, a 4-port MUX to an 8-port MUX, and AP1 might still end up being your out, but it changes the other application layouts down the line. So your out ports are predetermined and you can't change them. They're also the port that you source for the port that wants to get all the MUX traffic. So in this scenario, we technically have 5 ports, right? 1, 2, 3, 4 in, and then 5 is our out. So on AP 1, 2, 3, and 4, those are we'll say, connected to our servers that are doing these purchased and sell orders. So we're going to source Ethernet 1 to AP1. We're going to source Ethernet 2 to AP2 and down the line. And then for the port that goes up to the exchange, which is going to be ET5, we're going to source AP1 because that's the port that's sending out our MUXed traffic. And we can do a live example of this later if that is in any way confusing, but hopefully as I continue to go through this, that makes perfect sense. Use the show MUX status to find which ports are the out ports. That's the command that I was trying to come up with earlier. Other Metamux operational tidbits, right? So that's how you would enable everything, and a brief example of how you would configure it using the various sources. And that is it, by the way, right? Like it's actually that simple. You set the mode here, and then you configure your interfaces, you're done. Like that's the configuration that you use in order to actually do this. So let's run through an actual example where we're going to. We've got a connection to the exchange on SFP1, which connects to Ethernet 1. So as we go through the lines here, each of these Ethernet interfaces are our inputs. They're going to get a source of ET1 because they all want to know what's coming from the exchange. So 2 through 8 all have a source of ET1. All of these AP ports get sourced from these physical interfaces. So what comes in ET2 needs to also go in, we'll say AP1. And that's how we take that data and make sure it goes into the FPGA. And then we find our FPGA out port and ET1, our connection back to the exchange. That's the one that we want the out port connected to because that's our MUXed data. Right, and so here's kind of the the more step by step of that, right? The exchange needs to be sent down to all of the trading servers. Um, we know that the trading servers have to all go back out ET1. So our high level config is that we don't need the mux to get from the exchange to the servers. From here to all of these guys is one to many. That's easy to do. And then we need the mux to go back. Our mux config here, mode 4x8, because there's only 8 ports involved here, so we don't need anything. We can't do anything less than that. That's our minimum requirement. No shut it. We look for our out ports. We see AP1 is out. We configure ET 2 through 8. Those are all sourced by ET1. That's how we're getting data from the exchange to our servers. To get the data from our servers into the mux, we source AP ports with the physical interfaces. So AP1 with ET2, AP7, ET8, and then ET1 gets our out-facing port that we did over here, source AP1. Counters, right? So we've configured it.
Hey, Jonathan.
Yes.
Sorry to interrupt. Quick question. I know you said that the applications, in particular Metamux, adds latency, right?
Yes.
But does that add bidirectional latency or only latency when you're using the FPGA? So in other words,
that is unidirectional
one
latency.
to N.
Yep. Yeah,
What's that?
That it is absolutely unidirectional latency, and that's a great question.
Okay,
So
fantastic.
the exchange takes in the traffic on ET1, 2 through 8, all source ET1, no FPGA needed there, right? So we have our between 4 and 6 nanoseconds of port-to-port latency, and then the return, the muxed traffic, is the only thing that gets that added latency because it has to run through the FPGA in order to get it out ET1 as a muxed signal. Yeah, no, great question.
I got you. And then AP1 is going to be an in and an out.
Yes, yeah. You'll typically find that, you'll see down here where when we grep for it, you can grep for the out to find which ones are your out, but you'll see that it's also an in, and it can do both of those functions independently. Absolutely.
Gotcha. Thanks.
So after we have everything configured, and now we want to look at stuff, right? Like, are there errors? What are the errors? Are we buffering? How many packets in? How many packets out? Stuff like that, right? Show Metamux counters verbose is your best friend here, right? So we do an RX count of all of the packets that came in. We have buffer counts. We have our drops. We have errors, MTU errors, storm drops, because you can configure storm control on these devices, although we're not going to touch that in this particular session. Just know that it exists. And then transmit packets, right? So a really easy one. When you're muxing traffic, all of your in traffic should equal your out traffic. So if we add all of these numbers up in this RX packets column, it should equal this exactly. And I say that because there's no drops. Now, if there were drops, there's going to be a discrepancy in the values there, but we don't want drops. Drops are bad. That said, buffer, right? The fact that packets are buffered isn't necessarily a problem. Again, these are all 10 gig interfaces. So that's a really important thing to keep in mind. You have 7 10 gig interfaces coming in and one 10 gig interface going out. Traditional switching logic says you're going to have buffered or dropped packets when you have data running at high volumes across all of these links. So something to be aware of. In some cases, the solution to a customer problem where they're getting drops due to high buffer counts is, well, you need more muxes and less, in interfaces. So instead of doing an 8x1 mux, maybe you do a 4x1 mux to reduce that ratio of in to out, right? This is just a brief description of what each of these is. They should be relatively self-explanatory, right? RX packets, everything coming in. Drops is anything that we dropped due to the input being greater than what we could handle. The buffer column is the total number of received packets that are being sent through like the slow path. That's how we're buffering things. RX errors are packets that where we detected errors on the given port. This could be BER, CRC. Again, we're still going to pass these, right? Because this is functionally a layer one device, but we might want to know that, we're seeing errors on AP1, because if the device that's receiving errors is receiving from all of these inputs, right? So how do we quickly try and figure out which one of these inputs is the one that's sending in errors? TX packets, total packets out. And there's a TX errors that's not on this page, but again, you would surmise that your TX errors is the culmination of all of these errors. What else do we got? Oh, buffers in MetaMux, yes. So as packet aggregation scheduled packets arrive on the multiple ingress ports and we need to send them to a single egress port, there's a strong possibility of a collision occurring by default, right? In the case where there is a collision, we start selectively queuing the packets, or in extreme circumstances, we might have to drop them if there's too much going on at any given point in time. Otherwise, all packets are strictly prioritized by order of arrival. So first one in means first one out whenever possible. Following that, it is by lowest ingress AP port number. So there is some prioritization that follows that first in, first out if and when we need it. And then we can also change that to round robin via the CLI. We can also completely disable packet buffering per multiplexer, so that is possible to do, in which case we will drop collided packets. And you've got approximately 16 kilobytes packet buffering per ingress port. How do we handle jumbos and runts in MetaMux? The really short version is we don't take runts, and we don't really support jumbo frames that well either. Not through the mux. Through regular patch panel, it's perfectly fine, but muxing them, we end up truncating them. So you can see here, we did a ping, we did a repeat with a size of 9,000, and you can see that we had RX errors, we had MTU errors, and you can see that we actually we still transmitted all the packets, they were just truncated. Yeah. And then we have a couple of common scenarios. This is where, yeah, see, I knew I started putting reference case numbers in here. So we have a customer who observed a BGP flap with the exchange. Now, the 7130 isn't doing BGP, but it sits between the exchange and the local router that is running BGP. And the customer in this particular case has a newer 7130, so they're running the MetaMux 3.x series. So what are some things that we want to take a look at? Interface flaps, right? If our link up to the exchange physically flapped, it makes perfect sense that our BGP session went down. What are reasons why that could have flapped? Could be low light, could also be related to PCS errors. And that has been alarming to some customers in the past, because especially if they were running MetaMux 2 dot something and recently upgraded to 3 dot something. In the older version of MetaMux, we had some safety mechanisms where we would do transmitting on the idle times on a link in order to keep it up. And we had to remove those safety mechanisms to get that latency gain that I showed a few slides ago when I was saying that, we were up to almost 90 nanoseconds through the FPGA on the oldest platform, and we're down to like 39 nanoseconds on the newest platform. That newest platform running MetaMux 3.x compared to 2.x on the prior. One of the reasons we were able to do that is because of better hardware, but the other part was because we improved the software from a latency perspective. But once those safety mechanisms were gone, it opened up this possibility where if we pass through enough PCS errors from our local links that were muxing traffic up to the exchange could read that as a bad link and flap the link. And if it flaps the link, BGP bounces. So it's just something to be aware of, where bit level errors can lead to an interface flap on your exchange facing port, even if it didn't cause a flap on your server facing ports. because it's a culmination of errors from multiple that led to the flap of one. Specifically, we were actually seeing this in a case where a customer was doing maintenance on like three of their servers. They always did their maintenances in groups of threes. And whenever they did the maintenance on these servers and they rebooted them all at the same time, there were enough errors on the links sent up to the exchange that it caused the whole exchange session to drop. So something to be aware of. Um, Another common scenario is a single mux gets into a stuck state. So when I say a single mux, isn't the whole FPGA a single mux? But this ties specifically to having like two 8x1 muxes in a 16x1 mux. So we're talking about an individual 8x1 section of the FPGA. And we've run into cases where just one of them stops working. And again, PCS errors wound up being able to cause some problems. And we have made a lot of improvements to this over the well, since Mux 3.x got released, really. 353 has a self-recovery fix for this. So if you're running into this particular problem with customers that upgraded to Mux 3, but they're not running this code, as many of our customers are apt to do, strongly encourage them, to upgrade, reference our, that we have this fix in place. And I don't think we have a slide on it, but now that I think about it, I should add one. We publish all of our bugs in the release notes for a given version. So if you go to the newest version of code and you check the release notes, you can actually see what bugs were addressed in that fix, as well as what bugs were addressed in any previous fix. So all of that's available right in the release notes for any given version of Mux or MOS or any application, etc. And then a third one, because spent some time talking about buffers. So what happens when you have packet drops due to oversubscription, right? The first is making sure that that's actually what's happening, right? So we need to take a look and see how many packets are being buffered, but also do our best to take a look and see at is it a particular port? Is it multiple ports? How all of that's working. When in doubt, when we're dropping packets like this example here, where it's just all across the mux, we're dropping packets. And even though there's errors on one, those errors are probably not causing all of our packets to be dropped across multiple interfaces. This is just too much traffic into a single out. Yeah. So increasing the number of mux cores, that's what we'll refer them, or we refer to them as, like previously, where we had a single mux in a stuck state. You can identify which muxes belong to what group by which core we associate them with. And that's, in this particular example, this 0 following the mux. It's always that number that follows. So you'll have a 0, a 1, a 2, a 3, however many the mode that you're running for the MetaMux application. So yeah, increase the number of mux cores, reduce the number of in to out, right? Just adjust your ratio. If that's not possible, they might actually just need to work on reducing the ingress rate for packets that are hitting the MetaMux. Because again, all the ports are 10 gig in and out, so the customer needs to be aware of that. And that's it for MetaMux. So before I start MetaWatch, I'm going to give an opportunity for quick questions.
Yeah. So do you see? I know that it was mentioned that really only financial customers use these. Do you see? Because it seems like this would be the ideal for TAPAG as well. I mean, single MetaMux or whatever to, uh, you know, to multiple tool, single or multiple tool ports and just a bunch of tap ports
Yeah, it makes sense.
going down.
So I
But I guess
haven't.
it's because of scale, right? Like
Scale is
high
the big
speed.
issue
No,
there. Yeah,
yeah.
exactly. Because you can't in a regular EOS TAPAG switch, you could run a port channel and do 4 10 gig interfaces and logically combine them into a single 40 gig as your out port, right? And you don't have that capability here. So I haven't seen customers prefer using these over like a 7150 to do TAPAC related functions, or like a 7280, I think is another common one. I actually forget what the common EOS platforms for TAPAC is. I think those two are legitimate though.
Yeah,
Um,
7280 because of the deep buffer.
that makes sense.
Yeah.
Um, yeah, so I haven't seen a whole lot of it. It doesn't mean that it's not being done, but I would imagine the sales team would steer them towards the platform that has bigger buffers than this one does, better throughput, and is running EOS, which is more Arista centric, right? Arista had TAPAC switch before we acquired Metamako, um, so it might have something to do with it. That said, yeah, it's certainly plausible that you might run into a customer environment where they're using it for that exact use case. I definitely won't discount the possibility because it does seem like it would work perfect for that. And I 100% expect it to be a feature on the EOS 7130 hybrids that come out in the future. Like that just makes perfect sense.
Yeah, that makes sense.
All right, cool. Without further ado, that takes us to application number 2. And it's a little bit of a toss up which one's more popular between Mux and Watch, but they're both very, very popular. Just leave it at that. They are the two number one contenders. So, what is MetaWatch? So, this is kind of that TAPAG that you were talking about, with a little bit more going on because we can do this inline tapping and replication to the FPGA, and we can add these really ultra precise timestamps, sub nanosecond, like I think it's 70 picosecond accuracy timestamps on the packets. And that's a big deal, again, if you're trying to determine whose data got here first, right? So you have this multi-port capture and aggregation, and this is where we get into really deep buffers, especially compared to the MetaMux. They're outstandingly huge. So this is a slide about why do we need or care about super accurate timestamping, right? And I'm really not going to go into the long story of it. It's a great slide. I highly recommend reading through it in the interest of not monologuing too much. The point still stands, especially from a high frequency trading environment, that if you can prove beyond a shadow of a doubt whose data came into the device first, and whose data gets, like, who gets to buy the thing at the cheapest amount, like that makes a world of difference to these guys. So I'm just going to leave it at that for now, but it is a really good scenario. Highly recommend reading through it later. Platforms. So you'll see these on the 7130L and K series. Again, those are the types of FPGAs that are installed in the DUTs. We support time stamping for 1 gig, 10 gig, and caveat 40 gig interfaces, right? These are our L1 plus devices, that the way that we support this sub nanosecond timestamp precision via the MetaWatch application is I can't words today. They support sub nanosecond timestamp precision via the MetaWatch application, and we typically implement them as an inline active tap for tap and replication to capture servers, etc. So when we're doing the active tap, we're still actually getting the original traffic through the device in 5 nanoseconds. We're just copying it into the FPGA, but that original data that's going port to port is still maintaining that basically original latency, which is really big. And then the same timestamp format is used across all the platforms. So even though there's different FPGAs here, the timestamp formatting is actually always the same. It even got picked up by Wireshark. Wireshark will actually understand our timestamps at this point. The note on 40 gig is if the correct MetaWatch mode is used. On the front panel, there's 4 interfaces with 10 gig that are connected with, we connected to 4 FPG or 4 AP ports, and we can, in very limited circumstances, get that to support a 40 gig throughput. So it's kind of rare. It's super specific. We'll have like cases, and I think there's a whole EOS article dedicated to just setting that up. The buffers play a huge part of this particular application. So when aggregating the captured traffic, because we're muxing very similar to the way MetaMux does, just not the goal here isn't speed through the mux anymore, right? Because we're not sending data up to an exchange, we're sending data to a capture server where we're just going to store it. It's just data, and the actual destination for the traffic isn't on the other side of the FPGA. This is just the inline tapping that we're doing. So we have huge buffers. And it's important to understand the trade-offs between the number of capture ports and the number of egress ports, because if you've got too many capture ports and too few egress ports, you run out of buffer, or you run into issues with bandwidth, you start dropping packets, things get bad, right? So how do we sort of mitigate that? Each MetaWatch core has two layers of buffering. You have these shallow per port buffers, which rarely ever really get used, right? But they're 40 kilobyte, and that's on a bandwidth of 10 gig write and 20 gig read for the K series. And then we have this deep aggregate buffer with a 40 gig write bandwidth, again for the K series. On the L series, we have, again, 40 kilobyte buffers with a bandwidth of 40 gig read and write, and then really, really, really deep aggregate buffer of 30 gig total divided per core, um, and then bandwidth of 120 gig for a write. So we can move a lot of data through these devices, and the buffers are huge. In order to make the best use of the buffers and reduce the risk of drop frames, though, it's still important to make sure that your size and bandwidth of the buffers within the application don't get overwhelmed. You don't want oversubscription. Um, so when you're avoiding that, again, you're paying attention to in versus out. That's really all it boils down to. There are some customers that ask, by the way, if these are dynamic buffers, if you can, move around which ports or which cores get more or get, what amount of buffer, and they're not. They're statically defined. So the way that you manage buffers per core is by changing which devices connect to which core. That's what you would do with, like, if core 0 is really full and core 0 has application ports 1 through 4, then you might take one of the high performers and not source it to application port 1 to 4 and move it down to like 5 through 8 or something like that. Right? You're doing it via config that way. We can provide data rate and packet rate limiting capabilities on all aggregated output ports. Data rate limiting enabled from the command line, works in megabits or gigabits. It's right there on the left. It's just bandwidth and then the value. There's not a whole lot special there. You do this from within the application config. We have a minimum limit of 1 megabit per second and a maximum for 10 gig. And then we can apply them in steps of just under a third of a meg. Packet rate limiting is enabled from the command line interface, and it works in the form of packets per second or kilopackets per second. And again, very much the same. You go into the application config, you apply the packet rate limiter, you call it a day. There's a minimum limit, again, 298 packets per second minimum, or 15,000 kilopackets per second as a maximum. And then you're applying in steps of, again, about 300, just under packets per second. If we are configuring both, you use whichever one's more restrictive. Size of the packet matters as far as like your data rate limiting goes, less so for the packet rate limiting, right? Buffers, how do you check them? So we have this command called show SD RAM status, and it shows you everything on the spot as of right now, right? So in this particular case, nothing's being used, but you can see we have 4 8 gig buffers with absolutely no buffer utilization. You can look at error counts as well. Error counts are less useful, but it's nice to have them every so often. Installing. I don't know why this is here and not in the other, but we're going to go through it in case I forgot why I put it here. The latest MOS versions get shipped with a compatible version of MetaWatch. In fact, if you're getting the regular ISO image, it comes with the latest version of all of your applications. If for whatever reason you need to install or upgrade, follow through the steps. SCP it from wherever you downloaded it to, some sort of server repository, right? Once it gets on the box, file is the like quote directory that you'll use when you use the install application. You know, file is your directory and then the name of it. Oh, installing a new CLI instance. I forgot about that. So after you've installed an application, you have to log out of the CLI and log back in. I'm glad that I did keep the slide for that very reason, because I don't think we covered it yesterday when we talked about applications. That's for all applications. And I mean, you literally just have to type exit a bunch of times until you're not logged into the 7130 anymore, and then SSH or whatever to it again, telnet to it again. You have to completely exit the CLI session and go back in. It's weird, it's quirky, just one of the little things to be aware of. Once it's there, choose a mode, right? So again, we've got our mode options. You've got a 4x12. You've got a 3x12 with, what is that? Oh yeah, 3 cores of 12 inputs at 10 gig into one 10 gig output. And then you have 12 inputs at 1 gig into a 10 gig output. Again, bunch of modes. I'm not going to just read from the screen. If you want to see what the modes are on a switch that's live, go into the config, type list modes. The asterisk there tells you the default mode if you do nothing. Time sources. This is a pretty important part of MetaWatch because timestamping, right? And so how are you going to super accurately timestamp a packet if you don't have a time source? So important things to know. Your MetaWatch is going to reference the time source that's configured on the 7130. So in this top example here, we're actually in the MetaWatch config, and it just needs to know if we're going to be doing free run. Don't do that. PPS, which is an actual oscillator clock that you connect to console, not console, not serial either, coaxial ports on the back of the unit. And then you've got PTP and system. You should pretty much only ever use auto, PPS, PTP, or system. Don't use free run, it's just bad. Auto is going to set the time source to PTP by default, just as a heads up as well. So this is MetaWatch taking data from the 7130. That means that in the base config of the 7130, not within the MetaWatch application, you actually need to have a time source configured there as well. And when you're in the base system, you'll be presented with NTP is a typically perfectly valid option as well. You should never have PTP and NTP configured at the same time on these units. It causes havoc because when they're both configured, they both try and run, and the clock starts jumping back and forth between the two. It messes with a watch. So just something to be aware of. Stick with a single thing there. So MetaWatch simultaneously reads the system time and then its own internal reference time. And it's doing this again just to maintain that super, super, super high accuracy. That and we need some way to get the data into the FPGA because that's what's making all the decisions. So our reference options again: PPS, PTP, system time, free run. Free run's bad. PPS is the most accurate, but you have to have a PPS device. You don't see it super often. PTP is your next best. Free run's bad. What happens if we lose the time source signal? So starting in version 10.6, we don't fall back to the system time if PTP stops being available. You'd actually have to configure that, like the time sort system has to be configured explicitly. If PTP was never detected, then we've never done any time stamping before, and the 7130 will wait for PTP to come up. And it won't send out any packets. So it's just kind of sitting there waiting to be spun up. If PTP was detected and then lost, it goes into holdover mode. And then in holdover mode, so after the PTP sync is gone, MetaWatch will run freely with the last known sync from the PTP hardware clock. This is really PTP specific, more of a just data point to keep in the back of your mind, unless you're already comfortable with PTP, because it gets complicated. But in that last option there, it leads to like no accuracy. So we stop sending timestamps, because if they're not accurate, we're not sending them. Troubleshooting stuff related to MetaWatch, and kind of specifically, at least for a few of these, is going to be about PTP. So if the time source in MetaWatch is PTP, then an interface on the device needs to be configured as a PTP slave. Otherwise, it's not getting that PTP data. The IP address of the management interface should be in the same subnet as the boundary clock. That's just, again, the way PTP works. You want them both to be in the same subnet. Check show MetaWatch status and show logging to see if PTP was in holdover mode at the time of whatever the issue was reported. Check for really any PTP messages in the show logging output. The show logging on these devices are really verbose. So if you can get the time of an issue, the logs surrounding that time are very, very helpful. If you come across a device and the PTP state is stuck in uncalibrated, it means that a potential master was selected and we're waiting for some calculations to complete. And until those happen, we're going to sit here in uncalibrated. So we can check PTP delay request and response flow, and we can look at the TTL, because if your TTL is dead, you're never going to get the relevant values from the master. This is all pretty specific, again, to PTP stuff. Don't beat yourself up too much over it. It's a thing to refer back to in case you need it, is how I think of most of the PTP things. Common problems for MetaWatch. So scenario one, where do we capture the timestamp and how accurate is it? Well, we've talked about how accurate it is. It's within like 70 picoseconds, which is awesome. Where do we capture it? So the timestamps are captured on the first byte of a packet on the ingress application port. We calculate the propagation delay between the ingress front panel and the FPGA application port automatically. So that means that even if there's a difference between how long it takes something to go from ET1 to AP1 compared to ET1 versus AP30, we calculate that difference, and we calculate it back to reference from where it ingressed on the 7130. So this goes back to the first packet into the 7130 is going to reflect that in the timestamp as well. Even though there's a delay between the front panel and the application port, we will calculate that difference. Yeah, so the main reason is, again, this avoids the need for the customer to try and adjust any offsets from, like, again, they might want to make sure that they're able to play fairly with their, like if they're a brokerage and they're selling to customers. And this eliminates that need. You know, they don't need to figure out the difference between ET1 and all of the AP ports. We will take care of that. We have white paper on the content and extreme detail of how we proved out the accuracy of our timestamping at these two links. We're not going to click on them here. Just know that they're there. Feel free to click on them. It's a fairly interesting white paper if you like clocks, I guess is the best way to put it. The next thing to figure out is, or not figure out, but other things that you run into somewhat frequently is, why are my timestamps not there? Why are they messed up in some way, shape, or form? So if you get a case like this, the quick things to check is the system time set up right. So again, if the time source is PTP, then somewhere we should have an interface that's in a PTP slave. We talked about the uncalibrated state for PTP. We mentioned never run PTP and NTP at the same time. It's bad. We mentioned the IP address of the management interface should be in the same as the boundary clock. Awesome. We can use the show MetaWatch status and logging to check for holdover mode and other issues during logging. We can check if we're dropping packets due to an exhausted buffer or due to rate limiting. Lastly, and this is probably the most important one, use packet captures. you can copy data from an application port directly to a management port and do a packet capture. So if we're connected to a capture server and the customer is saying, "Hey, on every 30 packets, I'm missing the timestamp," verify that, right? Copy the same data from the application port over to management 5 or management 6, do a TCP dump. Are we seeing that our timestamp is missing? If we're not, that's an issue on the customer side, right? Um, Great EOS Central article down here that goes into a whole bunch of more reasons why. This is just hopefully a quick summary of the most popular ones, or most frequent, maybe not popular. Tech support files. So we haven't actually talked about this a whole lot. How do you get them? We gave an EOS article for this. So instead of having to type it out to a customer every time, just bookmark that or know how to get to it quickly and just send them the link. Hey, we have a great article on EOS Central that you should check out here. I highly recommend referencing those articles, not just for this platform, but for really anything that we can, because we're trying to get customers to be proactive about using it. And we're trying to keep content up there, new and updated and relevant and fresh. And part of making sure that people use it is going to be that we point to it. So if you ever find an article on a thing that helped you, share that with your customer. You know, that said, what's the short version? Type show tech support, right? So we zip a file into Flash, and then you copy it out, and then so we tell them to submit the file there. They can submit it however they're used to submitting it. The one benefit of using this particular URL at the bottom is it takes you to this old MetaMako repository that actually has every show tech that's ever been submitted and tells you the serial number, like right in the get-go, tells you the serial number of the device that it came in on. So you can actually see immediately almost, hey, this device, we've gotten show text from it before in these other cases. Let me go look at those cases and see if it's relevant to what I'm doing. Um, Maybe they said that, they hit this issue once before and they couldn't remember how to fix it, stuff like that. So it's just a nifty little portal, but otherwise, TAC portal, FTP. They're big though. They're like 1.5 gigs, so don't expect them to email them to you. It's not going to happen. This is an example of what you see on the like new tech support archive. It'll say uploaded by so and so from this company. You can actually get a link just to the download and share it. Yeah, tells you the device, file download. This is just a snippet of what it looks like on that archive, this one did here. Um, After I go over the last couple of slides, I'm actually going to pull up a show tech really quick because it's one thing that I just earlier today decided we should add. So TCP dump usage and caveats. We've talked about this a bit, but I think it was worth having its own slide at the very least. So again, you could bookmark the slideshow, and in the index, you can see, oh, hey, there's a section on TCP dump, and it takes you right to here. You run it right on a physical interface. It tends to be lossy. It's low buffers. So whenever possible, copy it over to a management interface. Do it there. Right? But you can see your typical TX and or RX depending on whatever filters you apply. Right? It's best effort only, right? This is based off of sampling. It's only got a 512 byte debug buffer when you're doing it on the physical interfaces, right? And then when you're multiplexing traffic into an AP interface, how do we do it there? So the solution is just choose one of the management interfaces, source the relevant interface to that management interface, run the TCP dump on the management interface. And this is a walkthrough example of interface management 5, source an AP port, show the interface, its current state is down. We did a no shut, show the interface again. You can see that it's up. We can do a packet capture. This is what it looks like, et cetera, et cetera. And then additional resources. There's tons of it. There's so much of it. There's multiple knowledge bases. So I'm going to try and highlight the ones that I think are really useful or that are sort of repositories of information. So we have a knowledge base on EOS Central that makes this public facing, right? Customers can see this. It's a great place to link them to. It's got all sorts of different how-tos, FAQs, walkthroughs, etc. All of our user guides are right on the 7130 release portal. I can't give you a link all the way to a user guide, but this is the path you would take, right? Arista.com, support, software downloads, 7130, the release portal. From there, you'd find your relevant MOS version or application and look at the user guides. Not to be confused with the release notes. The release notes are also super helpful, but the user guides give you a step-by-step of all the different things you can do. In order for customers to see this stuff, they do need to be granted access by their sales team. We can override it with an exception, but we shouldn't. They should have the proper things provided to them based off of what their sales account says that they should have, right? So direct them to registration at arista.com unless it is super urgent. TAC, KMS, and PPP. This one is one of my favorites, and I call it the link to links. It's not actually that, but I will click it here. And it kind of makes sense, right? There's a topic title, a brief description, who the author is, where is it located, what's the topic, what's the link. And this is just fantastic. It's also, in case you can't, like, it's pretty decent in size. These tabs at the bottom weren't so great, but this page in particular is awesome. We have our TAC training. So this training is actually based off of training that was done by previous people before me. Vignesh is one. He's over on the West Coast, and he has a more detailed version of everything that I've talked about the past 3 sessions posted to this TAC training. If you want to go deeper into this stuff, that's where I would recommend you go next, is his 3 trainings. The other training that I took was Ben Harrison's training, which is leaning more towards introductory. So this is hopefully a good in-between between the 2. We've got 7130 reference doc. This is also what gets linked in the queue view header. I say worth the bookmark only because if a case comes in and it didn't get flagged at 7130, you might forget how to get to the reference document, especially if the customer didn't put the serial number in there. So that's the only reason I have it bookmarked. But this pops up at the top of every 7130 case in QView in like that gold banner, and it's got all sorts of helpful details in there. This is Go 7130 code names. It's just a link to that. I showed that yesterday, but it has all of your platform to app compatibility. Great stuff. And then we have some scenario-based training labs where if you can get your hands on a 7130 that's not being used by someone else and the relevant other DUTs are connected, you can actually configure some of this stuff. It's fun to do, it's just there's not many of them, so it can be hard to run through these sessions. That said, totally worth it, again, if you want to dive at all deeper into this particular platform. Aside from that, there's the Google Hangouts chat. You can click this link to go right to the chat room, or you can search for 7130 support in Google Hangouts chat. That's where we all are. There's also devs there. So sometimes you'll post a question trying to get myself, another SME, peers to just take a look and give you some guidance. And a dev might jump right in and say, oh, that's super busted. Can you get this, this, and this, and we'll file a bug. I'm like, oh, that was easy. Yeah, sure. Sounds good. That said, whenever you go into this chat, this isn't an official format, but I'm going to recommend it, especially if you're all going to be new to this platform. Getting all these details proactively is very helpful to the rest of us. And it helps you kind of build consistency. The other thing that's really nice about it is if you might start in the support chat and be advised that you should escalate it. And now you have all of these details are going to be relevant in your escalation. So you're just kind of doing a little bit of data gathering up front. Again, not official, but I'm going to recommend that format. Other stuff, labs. So the Nashua lab, there's a box. I think it's dead right now. It's DBE 337. And then there's a couple down in RTP, DBE 109 and 110. We have a few other ones. I've regularly used DBE 108 because nobody else seems to use it, which means it typically remains unbroken, which is great. And that's actually it for slides. So before I forget, I mentioned that I wanted to actually show what one of these tech supports looks like. And I just took a case the other day, so I just have to find the right one and I can show you. If it's the top one, okay, good. Here it is. I think that's them. No, maybe not. So hard. Nope, those are regular EOS tech supports. Here we go. So you will get a compressed file, and when you open it up, it'll look like this. And you'll expand it. I'm going to make this a little bit bigger if possible. Well, yeah. And you'll get something, yeah, that just looks awful. Like this, where you have individual files that contain the details that you want to look at. It's not the most fun, but for the most part, it
You're
works.
just sharing the
Oh,
Google Chrome or whatever, your browser. You're not
gotcha.
sharing the yeah.
Let's fix that. We should be able to fix that. Go here, presenting, stop presenting for a second, present a window, this, share. Aha. You should see a folder with a whole bunch of files in it, right? The top one should be ARP.
Yeah, we see that.
Okay, good. Thanks for letting me know, because yeah, that would have been awkward for the people that are going through the recording down the line. So yeah, you'll get a single file. Let me back up a step. Yep, thanks. And when you decompress it, it's just going to open into this. You're going to have your file name. It's going to be the serial number followed by some stuff that equates to the date, time, etc. And it's going to have, literal text outputs for a bunch of different things. So if you want to see interface counters, you double click interface counters. This is not relevant. And here's your interface counters. So it takes some getting used to, but it is all there. One of the things that, get out of here, that is nice is our logs. You can see daemon logs. Don't spend a whole lot of time in there. Some of the devs do. Messages is kind of like show logging system, right? If you type show log on a 7130, this is the kind of stuff that you're going to see. And they're very comprehensive. So I, again, strongly recommend narrow down the date and time that something happened. Check your logs. Your logs are in the log folder and then messages. You'll see that there's these zipped files that are also messages. So we use a log rotation, and every 7 days we'll compress all of the logs into a file and store them. And then we keep those for 7, I think. 1, 3, 4, 5, 6, 7. Yeah, I think for 7 sessions, and then we start rotating again. So you get quite a lot in messages. It'll go back for a while. Most of the other stuff in here in the log folder specifically is not going to be super helpful. If you really get into the 7130 platform, you can actually take this InfluxDB database data and your telegraph data here, and you can import it into a tool like Grafana and start looking at some interesting historical stuff. But again, unless you're going to really focus on the platform, I wouldn't get too far into it. That's more of a hobby, if anything. But yeah, interface counters, you're going to find that stuff in here. CPU info, you're going to find in here. Disk usage, inventory, show version, show run, that's in here. Yep, right here. So it's going to look a little bit different. You're not just going to have one file. This is a great place for if you haven't played around with grep in a directory. It's a great place to learn because you can grep for a particular thing, and then if you're doing it within this whole directory, it'll pull from whatever file where it's relevant. Maybe not so great for this one. I'm a big fan of it within the log directory, looking at messages, but other people that are better at Linux and grabbing specific pieces of data from a bunch of different files might find all sorts of stuff useful in here. Transceiver properties, verbose for the warnings, all that stuff, all the different things that I've talked about with the different show commands are all going to be their own individual file in here. So that said, any questions? There we go. All right. If you do come up with something, feel free to give me a shout. I'm, again, pretty attentive. I like working with this stuff, like answering questions or researching when I don't have the answer. That's always fun too. If you pick up a case you need a hand, ping myself, ping Ben Harrison on the East Coast if I'm not around. He's probably the next best go-to. West Coast guys, because I know there's a few of you on here. I know Vignesh is your savior. He's my savior most times. I don't know who else over there spends a lot of time with the 7130s, but at the very least, he's probably your guy. And I'm sure the other members of your team can help point you in a better direction if needed. Until then, I hope you all enjoy the weekend. It's Friday here. It's 20 minutes to 5. So I think unless anyone pipes up, it's a great time to let everyone go and be free.
The training, Jonathan. Really appreciate you doing this for us.
Oh, yeah, absolutely. I legitimately am very happy to do all of this stuff. And I'll probably post all sorts of more updates to the content, as well as probably re-record all this stuff in like 4 weeks when I kind of figure out all of the little details. But happy to help anytime. Seriously, ping me. Otherwise, guys, I hope you have a great weekend.
Hey, thanks, Jonathan. You too.
Thank you.